Hello, everybody. This is Mr. Gasco. We're going to be looking at the free response here for Unit 1. And so this is considered to be a 25-minute question, and we're going to show our work for each part. So they tell us, two students are each given a spherical balloon that has a string attached and is filled with an unknown gas whose density is referred to by the variable rho g. The filled balloons each have a radius referred to by the variable r and a volume referred to by the variable v, and the balloons rise when released. A small valve is fitted to each balloon to allow the balloon to be deflated in a controlled manner. Part A says, the string and balloon itself, but not including the gas, have a combined mass of m times b. Derive an expression for the acceleration of the balloon when it is released in terms of the given quantities and physical constants as appropriate. And they tell us that air resistance is negligible and has a known density of air. Okay, so this one is basically like a buoyancy problem. And so here's my balloon. And so we have our balloon, and it's probably going to be filled with some kind of gas. That doesn't look very good, but whatever. Okay, so let's go ahead and try to visualize this. We have a radius, and this radius is going to give us a certain volume. When we do, sorry, I got like the hiccups and stuff. When we draw our free body diagram, we have the force from the air, the buoyant force. So even though it's not in water, because this balloon has less density than the surrounding air, there will be a buoyant force acting on it. So here, and then we have the gravitational force pulling it down. And they want us to derive an expression for the acceleration. So we're going to look at Newton's second law, which says the net force on this balloon will equal to m times a. Alrighty, so let's go ahead and see here. Well, if we look at this, the buoyant force minus the force due to gravity will give us the mass times the acceleration, but we're going to have to be careful here. We're going to need to expand all of these terms because they want us to talk about these variables here in our expression. So we've learned that the buoyant force, which I'm going to call FB from here on out, which can get a little confusing because we have a balloon, but it's really the buoyant force, is given by the density of the fluid some object is in. So in this case, it's going to be the density of air times the acceleration due to gravity times the volume displaced. So because this balloon is like occupying space in the air, it's going to push out some air out of the way, which in this case, the volume displaced equals the volume of the balloon, which they told us is just V. And let me know if you have any questions so far, Sarah. And the density of the fluid is the density of air. Okay. So we can go ahead and rewrite this technically. The buoyant force will be rho A times G times V. And this volume here is variable, but that's not a big deal. We can use it as our variable to represent the balloon. Okay. The gravitational force of this balloon is going to be equal to m times g, but we have to be very careful because this is the gravitational force on the rubber shell of the balloon with the string plus the mass of the well, I think they don't give us the name, right? Yeah, the mass of the gas. So we have to be careful here. The mass of the system is going to be the mass of the balloon and the string, which they tell us is mass B with a capital M. And they told us not including the gas, because what's going to change here is the mass of the gas. Okay, so we have to be very careful. This is going to be the gravitational force on the system. That's like the fancy way of saying it. It's really just the weight of the air and the weight of the balloon. So here we have to expand this part. So the mass of the system is going to be the mass of the balloon plus the mass of air or the gas times the acceleration due to gravity. But we're not really allowed to write the mass of the gas here. But we can write it in terms of the density of the gas times the volume of the balloon. Does that make sense so far? And let me know if I lost you there, Sarah. Okay. All right, so we can go ahead and set this all up. We can go ahead and substitute for these two terms, and this expression becomes rho of the air times the volume times G, this is the buoyant force, minus, welcome Mila, we're going over the free response here. And so just to kind of run through it again, we have a balloon and they tell us that it's filled with some unknown gas with a variable, with a density represented by the variable rho times rho G. The balloons are filled and they have a radius referred to by the variable r and a volume referred to by the variable v. And the balloons rise when released. So there's going to be an acceleration when released from rest. And a small valve is fitted to each balloon to allow the balloon to be deflated in a controlled manner. They tell us the string and the balloon itself have a combined mass of capital MB. And they want us to create an equation for the acceleration of the balloon when it is released in terms of the given quantities and physical constants as appropriate. And they tell us that we can ignore air resistance, but it does have a density of rho A. So let me know if you have any questions so far, but we're going to try to use Newton's second law here to get that acceleration. And there's really only two forces on this balloon gas system. There's going to be the buoyant force from the air that pushes it up, and the weight or the gravitational force as we usually call it. And the difference of those two is what's going to give us the net force, and we can set that equal to m times a. So now we have to go on side quests. We need to get the buoyant force and the gravitational forces in terms of the variables that they've given us. And so we've learned that the buoyant force is the density of the fluid that we are displacing, in this case, the air, the acceleration due to gravity, and the volume of the fluid displaced, which in this case is just going to be the volume of the balloon, because this balloon is going to occupy that space and push the air out of that space, and that volume will be equivalent to the size of the balloon. And so here's our expression for the buoyant force. To get the gravitational force, we have to be careful, because in here, the weight, bringing this stuff down, is going to be the weight of the air along with the weight of the balloon. So here I went ahead and said that the gravitational force is the mass of the system times g, where the mass of the system is the mass of the balloon and the mass of the gas inside it. And then we multiply by g. Now, because m of the gas, the mass of the gas, is not a variable that they want us to use, we have to do the substitution. We can remember that the mass divided by the volume is the density, and we just rearrange this and say density times volume is mass. And so we get here the mass of the balloon, and I should really write that as a capital M. Plus here, this is the effective mass of the gas. It's going to be the density of the gas times the volume of gas that we have. And then we'll multiply all that by G to get our weight. So putting this together, we get rho Vg, that's the buoyant force, minus, and then here I'm going to go ahead and put it like this. Oops, that should be a capital. And so you had rho A. Yeah, we can even rearrange this here, and I'm going to do that in a bit, just so that we can show we know how to do algebra. Okay, and I'm sorry, the breakout rooms had been blocking the chat. And we set that equal to the mass of the system times A. So here we'll need to kind of remember that little scenario. Okay, so what can we do? We can factor out a G, and we get the density of the air, and we can even, we have to be careful. Rho V minus capital M. And I'm just going to distribute that negative. Minus rho G V, or rho of the gas times V. That can get a little confusing with rho GV. And all of that is going to again be equal to the mass of the balloon times the mass of the gas, which is rho of the gas times V. Let's set that equal to A. Any questions so far? And we can go ahead and just kind of leave it. And we don't need to do too much algebra. In this case, as long as we just get A equals and all our variables show up, I would say we don't need to rearrange this expression too much because we are on a timer, right, with a College Board. And as long as we put down the correct ideas, for instance, here we could say rho A minus rho G times V minus the mass of the balloon all over the mass of the balloon plus rho of the gas times V. We have our acceleration. Ta-da! And so let me know if we have any questions there, and especially if I made a mistake. I was taking a little nap here and I feel a little groggy.
Hi, sir. I just have a really quick question about the AP exam, because I know like APUSH, right? There's specific formats that they want the free response questions to be in. So is there anything like that for the AP Physics exams?
No, as long as you answer the question, you're basically it. So we derived an expression for the acceleration. So here's an equation for that. They're going to be checking if you're just applying the right principles. Newton's second law, buoyant forces, the application of density. And so we can even look at the scoring guideline here to see what they're looking for when grading this. So let me do a quick little new share here. And so this should be Physics 2 share. And so we can see the scoring guideline for part A. 1 point is for applying Newton's second law and using some parameters specific to the situation. So you don't even have to get it exactly correct. But if you knew that you needed to use Newton's second law, that's a point. 1 point is earned for the correct total mass. So recognizing that the mass in the system is the mass of the balloon plus the mass of the gas, which would be its density times volume. So this is really just what they look for. For using the correct buoyant force, which is rho of the air. That's the important part. A lot of people here would just leave it as rho or use rho G, but it's the density of the surrounding medium. And so literally this is how they score these in physics. And then Daniel, let me put you in a breakout room with the Physics 1 kiddos. At 6 o'clock, we'll swap again. But in the meantime, they're going over multiple choice part B. So sorry to do this to Daniel. Welcome to the review. All right. Okay. And then 1 point is for correctly including the term for the force due to gravity. And so this is kind of like the format that they're looking for. So thankfully, it's not as strict as AP US history. The literary or the liberal arts usually can be a lot more finicky than the sciences. Hopefully that answered your question. All right, let's go to the next one, but you're free to ask follow-up questions.
No, I just wanted to say, yeah, you did. Thanks.
All right. The first student is given a stopwatch and a tape measure and asked to use only this equipment in an experiment to determine the density of the gas inside the balloon from a graph of the data. Describe an experimental procedure that the student can use to accomplish this. Oops, so I don't think I copied over the graph. Let me go ahead and copy that here for B. So this one seems a little weird. This is actually, I think, part of like a challenging portion. But let's see here. So we have the net force, or actually a force. Wait, is this the correct graph? Because they tell us that they only have time. Experiment to determine the density of the gas. But what force are they measuring here? Give me 1 second. Oh, okay. So they want us to find out how to generate this graph here. How are we going to get the force? How are we going to get the volume? So if we want to measure the force or get the force acting, or I'm assuming here this is the net force, not the gravitational force, not the buoyant force, but the net force. Well, we need to measure the mass. We need to, for volume, we need to measure the radius at different sizes, measure the mass, measure the radius. We have a stopwatch, so probably measure the time to rise a certain distance. And I should be sharing on the OneNote here, right? Measure the time to rise a certain distance. Let's see here what else we might need, because we can get the mass of the balloon. Here we could say with a scale, which with a stopwatch. And then again with a meter stick. So something like this. Let me make sure I read the question and address that. So the student is given a stopwatch and a tape measure and asked to use only this equipment in an experiment to determine the density inside the balloon from a graph of the data. Describe. Okay, so we cannot actually measure the mass in this case, but we can measure the radius and the heights to get the accelerations and the sizes of the balloon and the time that it took it to move up. And then, like all experiments, repeat multiple measurements. No, I got invited to play Dota 2. Repeat multiple measurements and trials to minimize error. But really measurements, like we want to get an average radius, an average distance, and average time for each of these valve settings. So like, let's say I haven't let out any air. I measure the radius of the balloon like 2-3 times, get an average value, and then I let go of it and I set it to a certain height. And I measure the time that it takes it to rise to that height. And I do that like 3, 4, 5 times. And then we go ahead and let some air out and get an average radius to get an average volume. And then the same thing repeated again. We let it rise multiple times to get an average value for that time to rise. Okay, so let's see here what they were looking for in the College Board. Yeah, I think the graph is actually for the next part. New share, and then let's go ahead and see here how they wanted us to answer it. So we can go ahead and pull up the answers, and let's go ahead and look at part B. The student response accurately includes all the following criteria. 1 point is earned for measuring the radius, diameter, or circumference of the balloon. Bingo. 1 point is earned for measuring the time it takes the balloon to travel a measured distance, such as the length of the string. 1 point is earned for finding, ooh, my bad, I did not do this part. Finding the acceleration of the balloon from the measurements taken. I forgot to include that, right? We have the displacement, we have the time, but I forgot to mention that we should get the acceleration. So I missed a point there because we do need that acceleration from our equation to be able to like backwards solve for that density. And then 1 point is earned for taking more than 2 measurements, either multiple measurements of the same volume or multiple measurements at multiple volumes. So let's see here. Here's their short and sweet response. Use the tape measure to measure the diameter of the balloon and also to mark off a known vertical distance. Release the balloon from rest and measure the time it takes it to rise that distance. Repeat the procedure a few times, each time releasing some gas from the balloon. So not bad. Let me know if we have questions over that. And then the next question, C, Windows shifts. Let me actually copy this part down. Let's see. We go back to the OneNote. And let's go back to the OneNote here. Okay. So a second student is given a force sensor and the student attaches it to the balloon string. The balloon's volume and force required to keep the balloon at rest are measured. The valve is open, releasing some gas from the balloon. So I'm going to assume here like they like taped the string. Then there's the sensor to the string, or actually it's like sensor at the bottom and then the string and then the balloon. The valve is open, releasing some gas from the balloon, and the measurements are repeated. The graph shows the data obtained. Describe how the graph can be used to determine the mass of the balloon and the density of the gas. So this is the force necessary to keep it balanced. So this force here should be the difference between the buoyant force and the weight. And so if we look at this, we can probably use a line of best fit. We're probably going to have some kind of offset here. And you know what? We have the technology. Let's go ahead and get a ruler out. Oh, wait, I don't have a ruler in this method. That's right, because this isn't a tablet. But we could do a line of best fit that, so above as below, maybe something like that. Okay. Which looks a little weird here, but it looks pretty linear. The only thing, my concern here is that there's a negative force for 0 volume. So this probably tells me that this is the mass of the balloon and string, MB, when empty. Just by looking at it. Because if I have a force sensor, and normally if there's an upward pull, if I have a that's kind of like pulling it up. But if I have a negative force, I can assume that the balloon is pressing down on the sensor, and that's why we're getting a negative reading here for that 0 volume scenario. So if we look at this, we can go ahead and recognize, well, the density, the average density here is going to be something like the change in mass over the change in volume. So it looks to me like the density of this gas can be approximated by the slope of the line. So I'm going to say we probably want to analyze the slope of the line and then go ahead and that would give us the density. So let's see here what the College Board was thinking. Let me know if we have questions over that. Okay. Ooh, yeah. So let's see here. So we want to draw a line of best fit. Oops, I don't think. And so we drew a line of best fit. 1 point is earned for the correct expression for the measured force, which can be implicit if one of the following points is earned. So let's see here. Is earned for indicating that the slope equals. So here, really, I was making a big assumption. This is actually the combined density of the 2 objects kind of thing. The difference between the density of the air and the density of the gas. And then for indicating that the vertical intercept is equal to m, the mass of the balloon, times g. So we did get this point as well. I think here, that would also give us this point here. And then we really just kind of missed this point. Is earned for indicating that the slope equals rho a minus rho g. The line of best fit should be drawn on the graph where the force equals rho v, rho a. So this is the buoyant force minus the gravitational force. And then here, this volume is going to be our, here, let me go ahead and copy it over. And then we'll go back to the OneNote so that I can actually draw. So because this is an equilibrium, the net force is 0, and then we can just rearrange this so that we have what we're looking for. In this case, here's our slope m, here's our independent variable, here's our y-intercept, and then all of this, the force is going to be y. And so because of that, the important thing here to recognize is that this is the difference in densities, which we kind of had in our equation when we solved for it right here. but I kind of jumped the gun and just assumed, okay, well, the average density is going to be the slope, but that should also take into account that's the really like the difference between the density of the air and the density of the gas. Any questions so far? We're on this computer and we are recording. Okay, so let's go ahead and take a look here. So this is a free response question. We're going to show our work for each question here. And so this one should take hopefully 20 minutes. One section of a 5-meter wide irrigation channel that is filled with water contains an incline as shown. At the top of the incline, the channel is 3 meters deep and the water has a speed of 2 meters per second. At the bottom of the incline, the channel has a depth D and the water has a speed of VB. And the question is, in a coherent paragraph length response, explain how the changes in the channel affect the pressure of the water in terms of the energy changes in the water. So as soon as we're talking about water, pressure, and energy, we should be thinking Bernoulli's equation, which is intense. It's going to say that the pressure, or really the pressures, so we have what is called the static pressure, or just the pressure of this fluid existing. And this is what people usually think of when we hear pressure. And then the dynamic pressure, which is rho v squared over 2, plus the hydrostatic pressure, rho gh. And what we are told is that the sum of these two terms, or these three terms, will be a constant in the AP equation sheet. Well, what does this mean? Well, really, it's going to be the sum of this is equal, like if I add those three terms, that number will be the same at the bottom. So we could say P1 plus rho V2 squared at 1 plus rho GH1 equals P2 plus rho V2 squared over 2 plus rho GH2. Okay. So what's going to happen? Well, chances are the area that this emerges from will be different. If we look at this, they did not tell us that this is equal to 3 meters. We don't know that for sure. We do know that this still stays 5 meters. And then let me just check here real quick. Okay, all right, no problem. Sorry, Marco. No problem, yeah, definitely. Okay. And so here, the area at the exit may not necessarily be the area at the inlet. The area at the inlet, or I'll just put it over here, is going to be 8, not 8, my God, I added these. We need to multiply. That's going to be 15 meters squared, okay? The area at the exit is going to be 5d meters squared, whatever d is for that depth, okay? So here, they just want us to explain how the changes in the channel affect the pressure of water in terms of the energy changes in the water. So what's going to happen? Well, this water is going to drop height. Because H2 is less than H1, the water will lose hydrostatic pressure. What we call rho GH, due to a loss of gravitational potential energy. Oops.
Wait, is 0.2 the top part?
Ooh, where do you see the 0.2? Because
Or no. If you're saying like H2, is that the like top? Like
I would say it would be the second portion over here, down here. This would be like station 2. This would be station 1.
Oh, so then how would H be more?
Because I fumbled. Yeah, there you go. Thank you. I appreciate that. So H2 should be less than H1. Thank you. Due to a loss of, thank you, no problem. Have a good weekend. Gravitational potential energy. Does that make sense so far?
Yes, thank you.
Now, if we look at this, there's probably going to be a change in kinetic energy. Because if we remember the continuity equation says the area at the inlet times the velocity at the inlet equals the area at the exit times the velocity at the exit. This is mass conservation. Now, we don't necessarily need to bring this into the equation just yet, because they told us to only consider energy. But let's think of it this way. We are losing gravitational potential energy. That energy has to go somewhere. Well, chances are it's going to be manifested in probably some change in kinetic energy. So we can probably say something along the lines in two ways. If we lose this potential energy, we're going to hopefully gain kinetic energy. So we could go ahead and say that VB is probably going to be greater than V1, because VB is what they're calling the velocity at 2. Since the fluid converts its kinetic energy or its potential energy into kinetic energy. Sorry, my brain's starting to get all fried up. Potential energy. I'm getting everything all backwards. Energy into kinetic energy. On top of that, if the exit velocity, if the exit area is less than the inlet area, then the exit velocity here, which would be given by the inlet area over the exit area times V1, here, this ratio would be greater than 1. So the exit velocity for a simple mass conservation approach would tell us that it would be the exit velocity would be greater than the inlet velocity. So we should expect it to get faster one of two ways. If we shrink the area, we got to still get the same amount of gallons through, but the only way it's going to do that is if it comes out faster because it has less area. Or we could say, well, chances are it's going to come out faster because it's losing gravitational potential energy, that hydrostatic pressure, and converting it into kinetic energy. And then explain how the changes in the channel affect the pressure of the water in terms of the energy changes of the water. Okay, so then now we need to talk about P, which is the static pressure, the pressure of this fluid just existing, the collisions of these particles against themselves. So chances are this went down. Whoa, this went up. So it depends. It depends on how much this increases or decreases, because chances are this pressure could increase or decrease depending on the ratio. If rho V 2 squared is greater than rho G H2, what this tells us is that we gained more kinetic energy than we lost potential energy. So then that will give us a loss this will result in a decrease or loss of pressure. In this case, if the change in kinetic energy is less than the change in gravitational potential energy, then we're going to go ahead and have these particles increase their pressure on each other because they're not able to go as fast to alleviate the pushes on each other. So this is kind of like all over the place. Let's go ahead and see here what the College Board was thinking in terms of how we should answer this. So for part A, let me do a new share here. So 1 point is earned for the explanation that the drop in pipe means a decrease in potential energy of the water and thus an increase in pressure. Okay. 1 point is earned for an explanation that the channel depth means a change in speed. So we kind of said that with the continuity equation. 1 point is earned for and so I'm kind of surprised because this one here doesn't really talk about the change in energy, but they did say in terms of changes in the channel. So we could say that, okay, the decrease in the depth would give us, or it could also be an increase. They didn't tell us which way it worked out, but because we're changing the depth of the channel. Okay, sorry, I need to like mute Discord because it's getting really annoying. All these little. Because these changes in the depth, like if it gets smaller, it should go faster. If it gets bigger, it should get slower because of mass continuity. 1 point is earned for an explanation that whether speed, kinetic energy, and pressure increase or decrease depends on whether the channel depth increases or decreases. So I kind of said this, but not really. I wasn't specific about the depth. But I was saying here that, okay, if the velocity gained is much bigger than expected, we should expect a decrease in pressure because the overall terms here need to balance out. And then 1 point is earned for writing a logical, relevant, internally consistent. I don't think I would get this point. I was all over the place. That addresses the required argument, explanation, or question asked that follows the guidelines described in the published requirements for the paragraph length response. So here we could say claim A. A change in the speed and gravitational potential energy in the water results in a change in the water pressure in the channel. The evidence is the elevation of the channel decreases and the height of the water decreases. The reasoning here would be Bernoulli's equation is a statement of conservation of energy and states that the sum of the pressure, the kinetic energy per unit volume, and the gravitational potential energy per unit volume must be constant for a fluid streamline. Therefore, if the kinetic energy and the gravitational potential energy change, the pressure will change. And so here they could say a change in the speed and gravitational potential energy of the water will cause a change in the pressure along a streamline in the channel. The elevation of the channel decreases and the height of the water decreases. Bernoulli's equation states that the sum of the pressure and the kinetic energy per unit volume, that's the dynamic pressure, and the gravitational potential energy per unit volume, that's the hydrostatic pressure, must be constant along a streamline. Therefore, if the kinetic energy and gravitational potential energy change, the pressure will also change. So, questions over that? Because this one seems kind of like straightforward, but also like, what the heck? So let me know here if we have questions over that.
So they don't want you to like necessarily have to say if it went up or down, you just say changed?
Yeah, exactly. They just want you to address that there is a change and see why those, like, kind of why those changes occur. So here, that's kind of where I felt a little stuck. If you notice, I was saying, well, it depends on this scenario here with the kinetic energy per unit volume. Let me just update the share here. So that's where even I felt a little confused, because it's like, okay, do we have to choose one or the other? Because it kind of depends on things. You know, this is the kinetic energy per unit volume, and this is the gravitational potential energy per unit volume. And I just happen to take a stance that if this quantity increases more than the loss of that guy, then because things still have to add up, let's say, for instance, this is, I don't know, 3, let's just say these are all a value of 3. This guy's going to drop down to maybe, let's say 2. If this guy goes up by 5, well, then we still have to add up to 9. So this guy would have to be 2. Does that kind of make sense?
Yes.
And that's kind of what I was saying before. It kind of depends. In mechanics in physics 1, generally, if this went down by 1, this guy went up by 1, and this should have been 4. In which case, this guy here would just be 3, and this doesn't change. Does that make sense? So in simple mechanics, generally, a change in potential energy results in a direct change in kinetic energy. But for a fluid, that is not the case. And so it just kind of depends. if for whatever reason this guy went up to, I don't know, let's say this went all the way down to 1, and then this guy only went up to 4. In this case, we still need to add up, and the pressure would go up here for this guy so that it balances out. What this tells us is we lost more gravitational potential energy. We went from 3 to 1, then we gained in kinetic energy per unit volume. And so in that case, to conserve energy, the fluid pressurizes itself. One way to think about it is, let's say I have a very steep drop off of water, and all of a sudden I have like in a pipe, and let's say I close that pipe. All that energy it has to go somewhere. So what will happen is it's going to lose that gravitational potential energy, and it's going to lose a fair chunk, H worth of energy, if you will. But if it's not allowed to flow and the velocity here is 0, then you're going to have a very huge crash of water as it smacks into the valve that is closed. And the pressure here is going to jump up very quickly. This is called, what was it, hydrostatic shock. And I think Juan shared a video about that in Smarter Everyday or Everyday Engineering. I can't remember which of those channels. But hydrostatic shock is when you abruptly stop the flow of water. It's been flowing and it has kinetic energy, but if you drop off that kinetic energy, that's going to result in an increase in one of these pressures. It's either going to gain high and you're going to spring a leak that the water goes this way in every direction. And that's because this pressure here shot up all of a sudden, because this decreased all of a sudden.
Could you also have the pressure like go down if both of those things went up?
This one here, P2?
Like if we increased, so like with fluids, if you increased height, the kinetic energy doesn't necessarily go down. You could make that go up too.
So let's see here. So let's say for whatever reason, kind of, I think, let me.
Like if you had, or like if you made the top part smaller, like smaller, then would it go faster? Or like how more?
It kind of depends. It depends on how much smaller you make this. So this becomes like a squared inlet over a squared exit. And I'm just taking this guy here times V1 squared. That's really this guy times rho plus rho GH2 plus P2. So let's say I gained a lot of potential energy. This guy's going to go up a lot. Now here, if I make it much smaller, like let's say I make the exit area really tiny, this velocity is going to shoot up really quickly, which is going to cause this kinetic energy to increase due to that decreased area to match flow rates. So what will happen is this pressure here will have to drop. So this part here doesn't even have to change per se. If you've ever stood up very fast, and this happens for tall people, like at a very noticeable rate. When I get out of bed very quickly, the pressure here is very low, and you can kind of like slow down the blood to the brain and you will feel lightheaded. This is that lightheadedness effect, if you will. You get up very quickly, the pressure in your blood is going to drop in your head because the blood has gained a lot of gravitational potential energy very quickly. And so the pressure has to alleviate itself to conserve that energy. I don't know if that answered your question.
Yes, that makes sense. Thank you.
If you happen to have a sudden blockage, you know, like let's say you have some kind of cholesterol or plaque.
Sound very good, sir.
Yeah, especially in that case, you're in for a world of hurt. And what will happen is this pressure here will drop, and that will cause a huge increase in the back pressure. Because you can kind of think of fluids as traffic. If all of a sudden there's a huge crash and the lanes have to merge, the people over here are all of a sudden slamming their brakes, and there's an accumulation of people over here in the back. But let me know if you have other questions. Otherwise, I'm going to paste the next part. Copied over the Zoom bar, right? Yeah, let me try to hide the Zoom bar. You know, I went from like a multiple monitor setup to a single monitor, and I kind of miss the multiple monitors, especially when I'm doing some stuff like this. But multiple monitors is just so cumbersome. Like, I don't know. And also they generate a lot of heat. Like that's something that I think some people kind of take for granted. Okay, so the lower part of the channel gets narrower as shown in the figure. And the shaded slice is a slice of water in the section of the channel that is getting narrower. The following shape represents the side view of the slice of the water as the water is moving to the right. On the shape, draw and label the vectors to represent the forces, but not components acting on the slice. Represent each force by a distinct arrow starting on and away from the shape. Vector should indicate whether the forces have the same magnitude or different magnitudes. Okay, so if we look at this, because this inlet area, if you will, is greater than this exit area, we can, and if we use like mass conservation or the continuity equation, technically there's a little density here. And these are inlets. But because if it's water, water is damn near incompressible. You need to apply like 1,000,000 newtons of force, and its volume is only going to change by about 1% or 0.1%. I forget the exact value. But a lot of times we just kind of consider water to be incompressible. And if it's incompressible, the density does not change. And that's why a lot of times we just kind of jump to the area at the inlet times the volume of the inlet equals the area at the exit times the volume of the exit. Okay, so this is why here, this is like the thumb over the water hose effect. As you put your thumb over the water hose, you decrease the area that it can come out through. And so to maintain mass flow rate or mass conservation, the volume or the velocity at the exit is going to be much faster. This ratio here will be greater than 1. So how does this happen? Well, if this fluid is getting faster, it's going to be accelerating. So there's probably a force from the back part here that is going to be greater than the force like in front of it, because we're going to assume that there's probably water in here. And all of this water here is pushing on itself in all directions randomly. Now, how do we label that force? Well, we haven't really given it a name that we've drawn in free body diagrams, but we could say the force from the water in the back, and that's going to push it forward, and the force from the water in the front. If this was a perfect vacuum, then this would just shoot perfectly unimpeded. But because there's probably water in the front, because, you know, water, like whenever we take slices of water, those slices of water are usually taken away from like a section of water, but it's still there. And then we have some normal force, which is from the, I guess, the floor here. And then we have some gravitational force. And as far as we can tell, the water does not accelerate up or down. So we can just say that those two forces are equal and opposite. Let's see here. I think that's about it. I can't think of any other forces. Can you guys think of any others? Let me know in the chat. There's some like the walls are gonna, I think, create a force that points inward, but I'm not sure how do we draw that, because we have an inward force from the wall and an outward. So like this wall's gonna push in like that. This wall's gonna push in like that, which would be like out of the page for us. So let's see here what the College Board was thinking. Let's do a new share. Let's pull up this and let's see here. For part B, 1 point is earned. Oh, well, there's our free body diagram. For a normal force and a gravitational force, 1 is up, 1 is down. 1 point for having the normal force and gravitational forces of equal length. 1 point is earned for drawing a pressure force to the right, which I don't know. Let me know. Would you guys give me that? Do you think we should get this point here for, because I didn't label it pressure. I just called it the force from the water. So let me know. Are you guys kind?
I mean, it went right, but as an AP grader, sir,
You wouldn't. Okay, all righty. Because really, we should recognize that. Yeah, that pressure. Sammy, you too. All right, I'll remember that when I grade your
Oh,
class.
sorry, sir. You got 100% veto.
I'm just no. I think really it's good to play devil's advocate here and be stricter than lenient. So we should really recognize that that pressure acting along that area is what creates that force. And so while it may be the force from the water, well, it's better described as a pressure. So I would say maybe not these two, but I think I would give us this a point here is earned for having the leftward force be less than the rightward force. And so I think that's good. This is their example here. And so I think that's it